number of cycles to failure originally calculated was based on what volume of air and binder. What if it was something close to that assumed correction?
Yeah, that's.
What are we correcting? What?
So this NF is based on.
That's a pretty big change.
Yeah.
We're correcting based on the 4-point bending, right?
Yes. I can tell you. So it's about, so essentially, I'm looking at the numbers. So for 5% air voids, for 11.5 VB effective, the C is 1. So pretty much, this is an empirical relation. I mean, this thing is an empirical relationship. So constant, this correction factor becomes 1 in these volumetric conditions. So inherent assumption is that for VA and VB of this combination is when the test is run. When the test is run. Even though we don't do that, by the way. We usually run the test at 7% air voids, 1.5%. But just to understand what that means, so constant becomes 1 in this combination of VB effective. Okay. All right, so let's move on. So we were talking about the cumulative damage concept. So once the NFs are calculated after correction, and then this fatigue cracking transfer function is used in this particular case, and these C1, C4, and C2 are used. Now for this correction, you really need to have field distress data to calibrate for this combination. So these are the Michigan calibration factors based on the studies that has been done in Michigan. So these are the C1 and C2 values, 0.5 and 0.56 for calibrated values, and C4 was kept same, and C1 and C2 are the same here, 1.2 and 3.33, and for top-down correction, this is 1,000. And those are the numbers that go here, C1, C2, C4, and all that. And if you actually look at the output of the, once you run the analysis, all these numbers, very nicely done, very, very nicely done. So all the inputs that you input, they're very nicely documented in the output, so you can keep track of what equations are used and all that. So these are some numbers from other states. So other states, these are national coefficients. These are what Arkansas use, New Mexico, Washington State, and Colorado use. And these are for fatigue cracking, bottom up, and this is for top down cracking, just for reference purposes. I put them in there. Now for rutting. Rutting equation looks like this: plastic strain divided by residual strain times Kz beta 1, 10 to the power K2, temperature K2 to the power K2 times beta 3, number of cycles to the beta 3. So here, K1, K2, and K3 are constant. You're supposed to keep them constant and vary the beta 1, beta 2, and beta 3 based on laboratory data that you have on these samples. And everything is based on the strain at the bottom, at the center, I'm sorry, the strain at the center of each asphalt layer in the vertical direction. So these resilient strains in the equation are the strains at the center of each layer in the vertical direction, compressive strains. Those are used to calculate the plastic strain, plastic deformation that happens in each of the layers, asphalt layers. And for this, we use something called flow number test, repeated load permanent deformation flow number test. In the flow number, you have a pulse and an arrest period, and a pulse and a rest period. So 0.1 seconds pulse, and there's a relaxation period in a sense. And at the end of each, there's an accumulated microstrain. That's the plastic microstrain. And we keep track of this accumulated microstrain from this flow number test. And then this is the slide I showed yesterday about the volumetrics. So this is one sample versus another. So you get a plastic strain, E sub P, as a function of cycles for different mixes, and then you fit that equation for the rutting to these to find beta 1, beta 2, and beta 3. And yeah, this is where I plotted the dynamic modulus master curves. So yesterday we were talking about these, remember? Here are the dynamic modulus master curves of these two. They have same, very similar. You know, if you don't do the calibration for rutting, then you will get the same number from them, which is not correct. So calibration is extremely important. So this is the equation for rutting, and these are the calibration factors, beta 1, beta 2, and beta 3 for rutting. These are the national regression coefficients that get fixed. Now, one thing I want to show you is, if you take the logarithm of the left side, logarithm of EP, logarithm minus beta, so this becomes like a summation now, minus beta 1 times A1 plus beta 2 times, let's say we put this number here because it's a constant, times logarithm of T, beta 3 times logarithm of N. So if you look at this plastic strain versus cycles data, this is the original data. If you take the logarithm of plastic strain, that's in the vertical axis, this graph looks like a linear graph, perfect linear graph, okay? So, and you can actually see that logarithm of plastic strain is equal to an intercept, which is A, let's say, plus B times X. In this case, X is logarithm of N. So the slope is B and intercept is A. So the equation looks complicated, but it's really nothing but A plus B times log N. It's nothing but this. It's not complicated. So if you look at this, this is kind of the intercept A, this portion. Beta is really related to the intercept. There is also, intercept is also related to resilient microstrain, what we call, which is the vertical microstrain at the center of each layer. So this is like the slope, beta 3 is like a slope of this line. Now you have another component here, it's based on the temperature. So when you run this test at a higher temperature, you would have another shift. I haven't shown it here, but you would have another shift. That is, the whole curve would go upwards. If you run the at lower temperature, whole curve will go downwards. So this beta controls how much there is a shift in vertical direction. So this is another description of a bit more details about the flow number test. When you do a confined flow number, you have confinement, we have the plastic strain at the end, and we have, this is what we use to calculate the curve here. Now, one sensitivity analysis, very quick sensitivity, one at a time sensitivity analysis we've done, I want to show. When you use a beta and beta 1 and beta 2, beta 1 and beta 3, 1 as the default, let's say this is the rutting curve that you get for 20 years. Now, we only run flow number tests at one temperature, so we did not vary the beta 2 because we don't have that data to shift. But what we did is, said, okay, let's change beta 1 from 1 to 0.06. What happens to rutting? So rutting actually went from here to here. So when we kept the beta 1, 1, but changed this to 0.7, not even 0.6, it went from here to here. Not even the same, because we had gotten 0.6 and 0.7 for those two from the data that we had. So clearly shows that beta 3, this beta, affects significantly how the rutting is predicted. That's for this particular structure. I mean, this applies only to this particular structure. I can't generalize that this is for all the structures, but this was input. So this is an important thing to know. beta only like test, point from 1 to 0.7, from here to here. These are the calibration coefficients that are used for different models here. So one thing that I have to mention here is some people, what they do is without running the material tests, material damage models, or those flow number tests or beam fatigue tests, they try to calibrate these beta values directly to compare with the field distress data. I don't think that's a good idea. It's not accurate. So I would also run the material tests and combine them together, and so we know exactly what we are calibrating for. Okay. One thing that I have to mention is this strain hardening approach that we use in payment ME. So the rutting calculations are based on these curves. So if you remember, our curves for plastic strain versus cycles in the lab is nonlinear. If in let's say in linear scale, but when you do it log, it becomes linear. What happens is this equation is based on the cycles. So there is a strain hardening effect. So as you go, if you actually assume that at certain temperature, let's say in January, if you are applying certain amount of traffic to go to this level, if you were to be running the same test at a different temperature, you would get a curve like this. So the payment ME uses a method called strain hardening approach to have like a discrete cumulative rutting calculation. So what it does is, first, using the plastic strain equation for any given time period, it goes to this, let's say number 1, calculates the plastic strain. For another temperature, it calculates the curve for another temperature would look like this, and curve for another temperature would look like this. So it finds the corresponding plastic strain and corresponding number of cycles for this curve, number 2, and then by just rearranging this equation to find n equivalent for this temperature, and then travels on this curve on this temperature, and then repeats the whole procedure over and over again. So it really goes like this zigzag type of method to calculate the rutting with time.
And then goes in reverse.
Goes in reverse, exactly. So when you go to, exactly, so it goes to reverse. It's a bit more...
go from 3 to 2 to 1.
Yeah, exactly. All right, so for thermal cracking, there's only one calibration coefficient. That is essentially K. So that calibration coefficient, you can't really calibrate it based on laboratory data. You really need to compare with the field data. We